Okay, so yeah, welcome everyone. Yeah, so tonight we've got Zoltán doing a talk on turning software into computer chips. So Hastlayer. Over to you, Zoltán. Thank you.
Thank you very much. So let me start screen sharing. And now you should be able to see my screen as well. And it's great to be here. It's great to be here virtually. It would be even better in person. And as I explained, Clive and the others in the very beginning, I actually visited Cambridge in February, which was unfortunately a little bit earlier than I got in touch with the organizers to bring this talk to you, which is something perhaps out of the ordinary for most of you, for most of us software developers and .NET developers specifically, because it's about something that you may not knew that you can do, namely create logic hardware, create pretty much chips as a .NET developer. So let's see. A little bit of interaction before anything else. I'm from a company called Lombic Technologies. Day to day, we are doing web development with the open source content management system called Orchid Core. So if you are a .NET web developer, I highly encourage you to check out Orchid Core. It's a great CMS, great framework, and a great community. And in these, we are the worldwide market leaders with the biggest Orchid team out there, with clients including Microsoft itself, or institutions like the Smithsonian Institution or the National Health and Care Excellence. Now, that's what we do day to day, but when we are not doing web development, then we are doing research and development like our Hastlayer project. And before going into details on that, let's talk about you. So let's suppose that you are working on an application where you are doing some kind of number crunching. And by number crunching, I mean some computationally intensive algorithms in the areas like the following ones, like AI, machine learning, including large language models, which are quite fashionable today, or something with images, image or video processing, computer vision, which have a lot of common things. Or perhaps you do some algorithmic trading on the stock market. Maybe data compression is something that you do. We are in Cambridge, so scientific computations usually have such aspects as well. AI, image processing, data compressions are things that usually are used there too. Or you do something in the sphere of cryptography or perhaps cryptocurrencies. Now, let's suppose that you want to have a fast application, a fast algorithm there, and it's not fast enough yet. So to make it faster, there are a couple of usual steps that you as a .NET developer can take. And first of all, you figure out why it's not fast enough. So you profile it and you try to optimize the algorithm. Let's suppose that you have already done that. When it comes to computations, a lot of the algorithms are already proven to be optimal, but that doesn't mean that you can't optimize while the logic is optimal. You can't optimize for the given hardware or for the given platform like .NET. Now, the next step is to parallelize it if it's not already parallel. So instead of using one CPU core, use as many CPU cores as your machine has. Furthermore, you can also parallelize on an operational level. So you can, in .NET, you can parallelize with tasks, which are kind of like threads, but will not exactly. We'll talk about that a little bit later. Or you can parallelize for operations like multiplications, doing more multiplications in parallel called vectorization. Let's suppose that you have already done that. Then the last basic step that remains is scale out, so using more hardware, or scale up using faster hardware. Now, let's suppose that you have already done this, or rather, there's not much you can do feasibly. So if you have unlimited time and unlimited money, then you can just throw that at the problem, but usually that's not the case. You have financial constraints, time constraints. You can have power constraints when talking about a custom data center or some embedded system. Now, the next step that you can take after these is to take a heterogeneous computing approach. So as .NET developers, your software runs on the CPU, but there are computing devices which are good with specific kind of computations. GPUs, I'm sure everybody knows, video cards, every PC has that if it has a corresponding screen, and you can use them for general purpose computing as well. And FPGAs. Now, let's talk about FPGAs a little bit more. If you haven't worked with FPGAs before, they are basically computer chips that can behave like any other computer chips. Within limitations, of course, because they have a physical capacity. They are not infinite. And that means that, for example, if you want a computer chip that accelerates or that computes the physics of a computer game, you can rewire an FPGA to do that. Or if you want to accelerate your algorithm recognizing cats in pictures, you can also configure an FPGA to do that. Now, even if you haven't worked with FPGAs before, I'm pretty sure that you have used them in some way. For example, if you Google something on Bing, then you have used them because Bing is accelerated by FPGAs. Similarly, Azure, if you did anything in Azure, most possibly you have utilized FPGAs behind the scenes because Azure uses them for accelerated networking. And FPGAs can be also found sometimes in household appliances like routers, or less household appliances like X-ray machines or MRI or PET scans, or even self-driving vehicles. Now, since we are talking about configuring a chip, basically creating a piece of logic hardware, you have to be a hardware engineer or possess hardware engineering knowledge to utilize these chips. And why would you utilize them? So what's in there for us when it comes to FPGA computing? The reason why we are looking at FPGAs is because they have some unique computing benefits, meaning that there are certain things that they can do better than CPUs and GPUs that we'll compare them with here. Now, this is a totally non-scientific comparison here, just to give you a very rough idea, but otherwise, of course, the devil is in the details. And let's talk about parallelism first. So how many things you can compute at the given time? Now, CPUs are, I would say, on the lower end here, because in a CPU you have something like 4, 8, maybe 32, 64 cores, but that's about it. With GPUs, on the other hand, you have thousands of little processing cores, which brings GPUs on the other extreme here. And FPGAs are roughly in between, although I would say that FPGAs don't really have cores per se, but still the level of parallelism you can get with FPGAs is roughly in between. Now, let's talk about the complexity of programs or complexity of algorithms you can execute on these devices. And again, CPUs and GPUs are on the two ends here. CPUs win because if it's software, you can run it on a CPU. Whereas the programming model of GPUs is much more limited. You can't just compute anything with a GPU. There are certain things that you can compute with them very efficiently and very fast, but not everything. And FPGAs are, again, in between. Although when it comes to an FPGA, you are not running a program on a processor. Rather, you are turning your program into a processor. And lastly, power efficiency. I would say that CPUs and GPUs are roughly on the same level here and usually on the lower end, whereas FPGAs are really power efficient. And the reason for that is that when you configure an FPGA to do something, then it does just that. It can't do anything else, but it does what you need to be computed very, very efficiently, because there's no operating system to run. There's not even an instruction set. Like with a CPU, it's just bare metal, what you need to be computed. And power efficiency, first of all, is, well, consuming less power, which might be a goal in itself if you care about the environment or if you have a power constrained embedded system, but it's also costs. Power not used means that first, you are not paying for the electricity, and secondly, you are not paying for the cooling. And that translates generally to cost savings. Now, there's a disadvantage though, and that's that utilizing FPGAs is really hard, because, you know, programming on a CPU is easy enough. Programming a GPU is something that nowadays pretty much anybody can manage as well, but using an FPGA is something completely different. You are not programming a CPU, you are creating a CPU. It's super low level. You have to think in terms of wires and logic gates and clock cycles. It's really something different than programming. But with high-level tools like Hastlayer, we intend to bring this complexity down onto the software development level. Speaking of which, what's Hastlayer actually? It's basically a tool that takes a computer program and turns it into an equivalent FPGA logic. That means that it takes a computer program and turns it pretty much into a computer chip. This is kind of our tagline here, although it's a simplification. We could also say that Hastlayer tries to get the logic out of that software of yours. It doesn't mimic line by line what it does, but it tries to get the logic out of it and tries to create an equivalent logic in hardware form. And of course, we are not talking about just any software. We are at a .NET meetup, we are talking about .NET. And we are indeed talking about .NET, not just C#, because Hastlayer processes the .NET DLLs, the assemblies. And that means that, at least in theory, any .NET language can be used with Hastlayer. We actually also have an F# sample among the samples. So to summarize, what we are shooting for here is to have the computing benefits of FPGAs for all of us software developers. That means that, well, first of all, you can get a very substantial performance increase over CPU execution for highly parallel compute-bound or memory-bound algorithms. Secondly, you do that with a higher power efficiency. And that means not just less power used for the same computations, but also lower costs. And thirdly, it's still software development as usual. So, a lot of talk until now. Let's see the whole thing in action. And let me show you how the whole thing works. So, now I'm switching over to Visual Studio. Please let me know if this is not legible for somebody. And what I'm showing you here is one of the example algorithms that we have among the sample packages. By the way, all the code that I show you here is up on GitHub. Everything from Hastlayer is open source. You can check it out in great detail, both the internals of Hastlayer and both all the other examples that we have. And well, this algorithm here is, as you may have guessed from the name, a highly parallel algorithm. It's not a real-life algorithm, but rather it's a kind of an exaggerated example of the kind of algorithms that are especially suited to be accelerated by Hastlayer with FPGAs. And this is what it does. Here's the core logic. Again, nothing particularly useful, but kind of a simulation of some number crunching. What happens here is that there's some conditional logic, which is executed 10 million times. And this is done in a parallelized way in tasks. Now, I guess most people here are familiar with tasks. If not, these are pretty much an abstraction over threads. We are doing multi-threaded computations here, but we are not working with threads directly. And that's quite useful because we are actually starting this many tasks, and this many tasks is 260. Now, when it comes to something like a 4-core CPU, .NET will take care of not to oversaturate that CPU. So even though we start 260 tasks, .NET will make sure that these 4 cores in a CPU stay busy, but we are not degrading the performance by starting 260 actual threads at the same time. Now, why 260 though? This is because Hastlayer will transform this into an actual hardware level parallelized architecture. And 260 kind of quote unquote threads or 260 implementations of this logic here is what will fit on the FPGA that I will use for the demo. Now, what we have in this class here otherwise is pretty much just some plumbing. We wait for all of the tasks to finish, and then we sum together their outputs, which will be the output, the end result of our whole algorithm. So pretty much that's it. Again, it's a kind of an exaggerated example of what works especially well in this computing model. And let's actually try it out. I will now switch over to a terminal. And the reason for that is because this is the board here that I will use for the demo. And this is actually an onboard computer of a satellite. Now, I wanted to bring you something even more curious here. And Hastlayer works in the cloud. So in Azure, for example, you can just provision a virtual machine with 1 or 8 compatible FPGAs, and you can use such huge high-performance FPGAs there. But what you can also do is that you can take such a little board, put a small Linux on it, put .NET on it, and put Hastlayer on it, and do something as you would in an embedded system. And this is the same hardware that actually goes in orbit for smaller new space satellites. This is what's used. And this is why I'm using a terminal, because, well, I'm connecting to the Linux running on this device. And now I'm running a demo script here. The demo script first starts up Hastlayer, and then it generates the hardware implementation that will be used in a later step. And once that's done, we are at this point now, it will start to execute that parallel algorithm as software. This board here has an ARM CPU and an FPGA on the chip, on the same chip. This is called a Zinc, by the way. So that ARM chip, that ARM CPU is pretty much the same thing as you have in your smartphone. And well, the FPGA is the special part. Now the whole thing finished, so we have some results. And here's the result. The CPU execution took around, 25 seconds, give or take. Now, let's take a look at the hardware execution time. If we scroll a little bit down, we will see the results here. Here it is. It took around 240 milliseconds if we take into account just how much the FPGA was doing the number crunching. If you also take the whole communication round trip into account, so including sending the data from the CPU to the FPGA and back, then it was around 325 milliseconds. Now, that's a big difference, and the big difference here is actually due to .NET, because, you know, there's JIT compilation, there are caches that were called on the first try, and if we scroll down, we also have a second execution here that shows us what happens if you repeat this, which would really be the real-life example. And in that case, it's around 260 milliseconds. So the FPGA, the FPGA execution was around 100 times faster. 260 milliseconds versus 25 seconds. Now, this is quite a large speed up just by executing our software as a different architecture. And you may ask that, okay, this looks nice, but I just showed you a very narrow view of how you utilize Hastlayer. How can you actually integrate this into the rest of your application? Because you wouldn't run all of your .NETs as FPGA, as hardware. You would only do that for the computationally intensive and highly parallelized parts. So there should be a rest of the application as well. And yes, there is. If we switch back to Visual Studio, in this program class, we can see how you would integrate your app with a Hastlayer executed part. And this is basically how it works. Well, first you create a Hastlayer shell, but there's just some basic plumbing. And then you do some configuration. The most important part here is that we are telling Hastlayer that this parallel algorithm class will be at least one of the entry points that we want to call from the host PC or from the CPU. Then we have the hardware generation step, which is basically this method call. This is where Hastlayer will generate the hardware implementation. I will also show you that in a couple of minutes. And here we also need to pass all the assemblies that our application uses. Now, this is just a very simple example with a single class that's in a single assembly. But you can have, of course, multiple classes with multiple methods. It's actually also a single method here. Your algorithm can span multiple assemblies. You can use parts of .NET's core library. Not everything, but what's compatible. So that's why we have this configuration step here. And finally comes the execution itself. As you can see, here's where we first execute the algorithm in its software form. And then comes the hardware execution here. And what you may notice in these hardware execution lines is that there's nothing really special. You just say .run. That's the name of the method that we have in our class. It's not, you don't have to name it .run, or you don't have to name the method run, but you just call that method and pretty much that's it. Hastlayer transfers the execution onto the FPGA. There's one step necessary for this to work before that, and this generate proxy async is that. Here we wrap our parallel algorithm instance into a dynamic proxy. This means that Hastlayer will be able to hijack the method calls and transfer them onto the FPGA. And by the way, this step can be decided on dynamically. So for every method call, you can create logic that decides whether to offload that computation onto the FPGA or keep it on the CPU. For example, if you are doing some image processing for smaller images, it might not make much sense to offload that to the FPGA because sending the data and receiving the data is so much overhead, and the processing itself is so fast that it doesn't make any sense. So you can write logic that says that, okay, if it's a small image, it stays on the CPU. If it's a 0.5 gigabyte image, it's pushed to the FPGA. So that was how you work with Hastlayer as a .NET developer. But perhaps you are also interested in how the sausage is made. And while you can inspect everything, from the code, since it's open source, let me give you a little bit of interaction there too. Well, first of all, this is the board that I've shown you. This is an FPGA board, as I mentioned, that has an ARM CPU and an FPGA together. And they are so much together that they are actually on the same chip with that little thing in the middle. This chip is called a Zinc. That's just a brand name. There's a family of such Zincs with smaller and bigger CPUs and FPGAs. And the smaller board goes into a bigger board, into those sockets there. We have such a bigger board because this is a development board. This is something for work and for such demos. It has like Ethernet connections. That's, by the way, one option to use from the FPGA side as well. And we had a USB port, some buttons, etc. But actually, you don't need all of that when you are on board of a satellite or something. And now let me show you how the hardware implementation actually looks like. So I will now show you code that a hardware engineer writes, but this won't be written by a person, rather by the automation of Hastlayer. So now let me go to a different editor, Notepad++ this time, and let me show you some more code. But this code here is hardware code. This looks like a program at the first glance because you have something called library here and a function and some if-else, which is familiar, but don't be mistaken. This is not a program. This is hardware code. And it's hardware code actually written in the language called VHDL. Everything that you see here will be turned into a piece of logic hardware, into gates and wires. Well, that can actually happen literally. So you can manufacture a chip from this code that we see here. But usually the easiest way to do that, if you don't have a couple of $1 million at your hand, is to use an FPGA and configure that FPGA with this hardware implementation. And if you scroll down a little bit more, we'll see something familiar. Namely, here, we have something with the name parallel algorithm here. And indeed, this block corresponds to our parallel algorithm class. Namely, what we have here are type declarations, something like a list of properties or fields in a class. So this is not the full logic, the full implementation of our parallel algorithm class, just some type declarations. But why I'm showing you this is because it has an index as well, an index of 0. And if we scroll down a little bit, we see exactly the same thing with the index 1, and then with the index 2. Now, can you guess where I'm going with this? If we scroll down a little bit more, we see again the same thing with the index 251. And if we scroll down a little bit more, we see the same thing again with the index 259. And now, do you remember that in Visual Studio, we started 260 tasks? Now, these 260 tasks are represented as 260 little processing cores here. So when Hastlayer turned that class with these 260 tasks being started into a piece of hardware, it created 260 copies of what's happening in those tasks. And that means that pretty much we now got a processor that has 260 cores and just computes what our parallel algorithm class needs. It can't do anything else, but it can do this very, very efficiently, very, very fast, and very power efficiently. So this is pretty much where the magic happens. Now, this is what we have. This is the state of the project, how you use it. What else is in there? Now, I've already shown you a little bit of hardware development, a sneak peek into what hardware engineers do. Now, this is another one. Hastlayer actually supports a platform called Vitis. It's a little bit .NET for software development in a way that it makes your code cross-platform. There's no such thing as being cross-platform in the hardware development world, because you can you need to support with your code every specific chip and every specific board with that chip. But still, this Vitis framework or technology of the FPGA company Xilinx is something like that. And with the help of Vitis, we can support a lot of available hardware, either already or with a little bit of work, we can support new ones. That includes high-performance cards that are available in the cloud or on-premises for data centers. And actually, all the major cloud providers, including Azure and AWS, have those FPGAs available. And secondly, we also support use cases like with this onboard computer that I mentioned here. And that means that you as a .NET developer can pretty much create applications for spacecraft or to be executed on board of drones. And this is not just a theoretical possibility. These pieces of hardware actually are on board of drones and on board of satellites already. We are working on bringing .NET into space too. Now, we did some benchmarking. So apart from this single example that I've shown you, we also have a couple of others. This is also detailed on GitHub, but just to give you a basic idea, when it comes to the huge high-performance accelerator cards in Azure, we measured a speed advantage between 4 and 34 times, and the power consumption advantage between roughly 20 and 120 times. Now, when it comes to benchmarking this, it's always comparing apples to oranges, because you are not comparing two CPUs, you are comparing a CPU with an FPGA, which is something completely different. We try to be fair in a way that these are high-performance FPGAs, so we compare them against a high-performance CPU. We also, and again, details are up on GitHub. We also did a comparison for the Zinc, where we compared this low-performance FPGA of the Zinc, this satellite onboard computer, to the low-performance CPU, the low-performance ARM CPU it has. There we had even nicer results. The speed advantage was between 25 and 120, pretty much what I've shown you here too, and the power advantage, something comparable. One curious thing that you can do with Hastlayer is to have your own number format. Now, probably you didn't do that before, because why would you create your own number format? But if you are working with machine learning applications, you perhaps already used something else than simple doubles or floats. Because in machine learning, it's especially interesting to have optimized numbers. Because, you know, when it comes to storing fractions as numbers, we as .NET developers usually just use doubles or floats. But for machine learning, sometimes much smaller numbers are enough, and you get a lot of speed advantage that way. Similarly, when it comes to scientific or engineering computing, those doubles or floats might not be accurate enough. And to solve such issues, there are other number formats. For example, the one called POSIT. POSIT was, or actually is, invented by a mathematician called Dr. John Gustafsson, who currently works on it in Singapore. He actually also worked at ARM, I think, at a point. Speaking of the ARM CPU on this board. And POSITs promise to be all around better than the standard flows that we use today. And what we have done is that we have created a .NET library that contains posits, so pretty much posit structs that you can use in any .NET program. And since the code is .NET is Hastlayer compatible, at the push of a button, you can also turn that into a piece of hardware. So pretty much, we now also have a POSIT processor. That's what you can also do with Hastlayer. You can create your own number formats and pretty much immediately create a kind of a processor that knows that number format. That's important because the CPU that you have in your phone or in your PC actually knows what that about the .NET double or .NET float type, where it doesn't know about the .NET type specifically, but those are standards that CPUs in general understand. Now, if you want to have more use cases, so there are a couple of use cases we know about and we have worked with users. We also have a couple of examples, a couple of use cases of our own too, but we would like to have more. So if you have some computationally intensive task that you are working on or some .NET application that is slow, please get in touch with me. I will be more than happy to see how you would work with Hastlayer. As mentioned, scientific computations is definitely one area where such compute acceleration is interesting. That's why we partnered with the Wigner Research Center for Physics too. And it seems that FPGAs are now pretty much generally available in every major data center, be it cloud or on premises. And by the way, it's something that the CPU manufacturers also discovered, because Moore's law won't go on forever. Because, well, we are reaching physical limits now, but still CPUs and processors in general need to be faster. And one way out of that is by improving the architecture with FPGAs. So you're pretty much adding an FPGA core onto your CPU. That's what I've shown you here with the Zinc, but that's what the two big CPU manufacturers also discovered, because Intel acquired the second largest FPGA company, Ultra, and AMD acquired the largest FPGA company called Xilinx. So Intel and AMD are now not just CPU manufacturers, but also FPGA manufacturers. So to wrap up, if you like this, and I really hope you did, please check out the SDK on GitHub. Everything is up there. The bulk of the code is in the SDK, but we have a couple of other related projects, related repositories too, with some other parts of Hastlayer. And be ready, because I think that FPGAs are becoming more mainstream. If you may remember, there was such a shift happening with GPUs too, because originally GPUs were just for accelerating pretty much video games and computer graphics. But then people actually in the scientific community noticed that, hey, we can use these GPUs for other computations too. And now general purpose GPU computing is a thing, and that's actually fully supported. Same thing is happening in FPGAs, because FPGAs started as something else. They weren't for compute acceleration originally. They were for testing and kind of simulating hardware designs, like a design of a CPU. But well, nowadays we are shifting, at least partially, over to compute acceleration. So thank you very much. If you'd like to get in touch with me, here are my details. And otherwise, check out the Hastlayer website, the SDK, as I mentioned, or if you are interested behind the company, in the company behind Hastlayer, check out lombik.com. And now perhaps we have a little bit of time for a Q&A. Clive?
Yeah, so well, thanks very much for the talk. I was just wondering, so how big I'm not sure how you measure the size of the FPGA stuff you generate, but how big a sort of hardware thing can you sort of generate using C#?
Mm-hmm. Yeah, that's unfortunately there's not a simple answer to that. But to give you an idea, the FPGAs are different as well, of course. It's not just about a single capacity number they have, but when talking about the most important capacity number, that's the number of lookup tables that an FPGA has. That's basically the size of the FPGA fabric. So the number of little thingies on the FPGA that you can utilize for your hardware. Now, this board that I've shown you here has about 100,000 of these, and that can fit that parallel algorithm 260 times. Now, those big high-performance accelerator cards, the one of those that I've mentioned, we benchmarked, has I think around 1.5 million. So 100,000 versus 1.5 million. Now the comparison is not as easy because there are a lot of other differences. It also has a bigger memory, faster memory, etc. But this should give you a little bit of idea of what's possible. But you can always try. You can try without investing into anything really, because the corresponding FPGA manufacturer specific software that we need and run behind the scenes, that's free to download as well. So pretty much you can take an algorithm, try it out with Hastlayer, run through the development tool chain of an FPGA manufacturer of Xilinx, and it will pretty much tell you if it won't fit onto a card. And if it does fit and you would like to try it out, you can just go to Azure and rent a corresponding virtual machine by the hour.
Cool. Thanks very much. Any other questions while we have Zoltán here?
Hi, Zoltán. Thank you for the talk. So, if I understand, if you ran at 206, the algorithm, the degree of parallelism of 260. If the task was significantly more complex, then would that mean that you would have that the board would support a lower degree of parallelism, but it could run that task?
Yes. So there are pretty much two dimensions here: the level of parallelism you can have and the complexity of your algorithm. And the more complex your algorithm is, the fewer parallel or the lower degree of parallelism you can have, and vice versa. This was a relatively simple algorithm. It can have a high degree of parallelism, but if you have something more complex, like some kind of image processing algorithm, then the degree of parallelism will be lower too. Actually, we have other examples as well with lower degree of parallelism, since the algorithm itself is more complex. Whether it makes sense to offload a more complex algorithm onto an FPGA depends on the specific use case. If your algorithm is highly parallelized, usually it does make sense if you can use a sufficiently big FPGA as well.
Thank you.
Okay, thank you. Anyone else with any questions?
Zoltán, can you call the FPGA from SQL Server?
Not directly, but if you can integrate kind of some glue logic into a SQL Server, then yes. While I use SQL Server daily, I didn't do much outside of SQL itself, but I believe you can pretty much load .NET DLLs into SQL Server as plugins, right?
Okay.
I'm asking that I'm not entirely sure. Anyway, if you can do that, or even if not, but you can, for example, interface via the command line with a different process, then you can integrate that. Pretty much what I'm saying is that while you can't communicate with the FPGA directly from SQL itself, you can, I believe, extend SQL Server in a way that you can integrate at least a small .NET app, a small .NET DLL that will allow you to do that.
Thank you.
Okay, so I guess if there are no more questions, thank you once again for a really interesting and informative talk. I'll be digging into some of that stuff tomorrow, I think.
Awesome, thank you for the
It was really
question.
good. So you're back with us in about a month's time, I think, on the 18th of October to talk about Orchard CMS. So that should be another great talk. So thank you.
Yes, thank you for welcoming me a second time as well. Let's hope that will be useful as well.
It will be very useful. Thank you. So I'll let you know about the recording and stuff via email. And yeah, thank you very much for everyone attending. Thank you very much for a great talk anyway. Goodbye.
Thank you.
Thank you, everyone.
Bye.
Bye.
Thank you. Bye.